Today I'll be doing a presentation on a question I came across in a book called Concrete Mathematics, 2nd edition, and that problem is called Lagrange's identity. And the man behind this problem is a gentleman by the name of Joseph Louis Lagrange, and let me tell you, this guy, total badass in the field of analysis, number theory, classical and celestial mechanics. And here's what that famous identity looks like. It's this nasty bit here with all the squiggles. What this is telling us here is that the sum on the left can be rewritten in the form on the right, and the goal here is to prove this identity is valid without using induction. Even though I'm pretty sure that this has been done tons of times in different ways, I'm going to show you how I did it. So let's go ahead and start with n equals 3, and I did this because why not 3? Could have been any other number, but for the sake of this video, let's use 3. And so let's go ahead and evaluate what's on the left side of the equation with n equals 3. And here we get this equation. And for now, we're going to set this as our goal and leave it at the top of the slide for now so we know what we're looking for. And now let's begin by evaluating the stuff on the right of the equation with n equals 3. And here we get this equation here. And this makes sense since we're essentially iterating through each sum and just writing the variables in. And an identity that I will be using in this process, I don't know the name of, but please ignore the fact that there are a, b's, and c's in it. They could have been any variables, but I will be using this here. And so using this identity, since we're just distributing each of the terms to each term, I obtain this ugly mess here. And I know you're wondering why I wrote it like this, but I'll get to that in a second. Next, we're going to evaluate the other proportion of the same equation, but distributing each term the same fashion. And then at the very end, we're going to be distributing the minus sign. So it would essentially be this, but with a minus sign in front. And we obtain this nasty bit here. And so this nasty bit and the other nasty bit here look like this together. And if you notice, there's something that is happening here that's quite special. So I see that I can cancel out these 1, 1 here, and these 2, 2 here, and these 3, 3 here, which essentially removes the diagonal from this matrix here. And so once I go through and cancel those bits, I'm looking at this and thinking to myself that this looks very familiar to what I had originally here. So let me go ahead and rearrange this. And so once it's rearranged, it looks like this. And now that I'm thinking to myself that this does in fact look very, very similar to what I had before here, what I will be doing is just going through each one of these lines here and factoring them to obtain this answer here, which is equivalent to this answer here, which is the left side of the equation, with this being the right side of the equation. And I did use this identity to go from this step to this step. And so the second proportion of this question does have a generalized version. And so I thought it was a bit strange to ask it in this fashion, but I went ahead and attempted it anyway. And so that next question is, prove in fact an identity for the more general double sum, which is this. And if you look at it very closely, it looks exactly like Lagrange's identity. And it does have the similar quality, but in this instance, we have a large A, large B in this other parentheses. And so this is how I would go about solving this problem. I would say that the problem that we have, I'm going to go ahead and say that it's equal to S, top right half, and I'll explain here in a second why I used this little triangle here. And we can begin to prove this by first finding the product of these two things in the parentheses, and so that looks like this. And so this is also equal to S, top right half, I guess, if you want to call it that. And so I decided to go ahead and use an identity here, this, which essentially establishes that the sum plus its inverse yields two more summations, one of which that says that J is equal to K, and the other one says that J and K are no longer dependent on each other. And so I will be using this guy right here to my advantage. And so if I go ahead and follow through with this identity here, I end up with this bit here, which is essentially the exact same as this up here. But I went ahead and rearranged it for the positive positive term and negative negative term. And this bit right here, since j is always equal to k, it just goes to 0. And so this right here is in fact 2 times my s top right half. And so next, what I went ahead and did is I distributed the summation to obtain 4 vanilla sums as the book would describe. And since now j's and k's are no longer dependent on one another, we can swap our j's and k's, which leads us to the form of the equation here, where I have essentially chosen this term and this term to resemble each other, and I've chosen this term and this term to resemble each other, but I went ahead and just wrote this term for this term and this term for this term, which is all still equal to 2s, top right half. And so as you can see, we have a bunch of 2's here, and if we go ahead and divide the whole equation by 2, we end up with this bit right here that is essentially the exact same. It's just now we're only looking at s top right half, and we have our summations here. I also went ahead and separated the summations by j and k just to save us a step. And so lastly here, if you look at this, we are essentially uh, removing the bits that have k's in them from the bits that have j's in them. And we did the same thing here on this side as well. And we did this just to kind of clean up the whole equation. And our last and final step will be to go ahead and swap out the j's for the k's here, since we can do that. And if you look at this, this is actually our answer here. And if you notice, it strongly resembles Lagrange's identity.